moving on another way. So before any final reviews or any classes, this is a question I always ask students. So what do we learn in this course? I will try to find a flaw. And we learn quantum mechanics, but what about those things? For each chapter, what am I talking about? So the first thing, we're starting from chapter 1, which is called early quantum mechanics, where we introduce the black body radiation, or wave theory, and Heisenberg's uncertainty principle. So all those that kind of gives you the idea that something in the microscopic world, they are quantized. They must be described by quantum mechanics. So this is chapter 1, where we talk about early quantum mechanics. But those are just the setup, the fundamental things for quantum mechanics. So following that, in chapter 4,
this may be a really stupid question, but when you say quantized, what exactly is that?
I mean, it's not a secret here. Just determined by the quantum number, like 1, 2, 3, 4. Cannot be 1.1, 1.2. Okay. So we follow chapter 4, where we talk about the formal postulates. So there are 5 formal postulates in chapter 4 and 1 postulate in chapter 9. Okay. When we combine them together, those are the formal descriptions for the quantum mechanics we are talking in this course. Okay. So we'll kind of go over some of them. So based on those 2 things, we actually taught you all the tools you need to solve the questions in quantum mechanics. So later on, we applied those things we learned in the 2 chapter to many different microscopic systems. Okay. The first microscopic system we learned in chapter 3 is particle in a box. You remember that? Particle in a box is the first microscopic word we learned. So after chapter 3, after chapter 4, in chapter 5, what microscopic system we talk about? Harmonic oscillator, great. And chapter 6, rigid rotators. Chapter 7, hydrogen atoms. Chapter 8, no, chapter 8 is approximation method. Chapter 9, chapter 10 and 11, molecules and chemical bonds. So those are the things we applied what we learned in these 2 chapters, and mainly from chapter 4 into those microscopic systems. Okay? And 2 chapters we missed here. One chapter is chapter 8, where we talk about approximation methods. Now we know approximation methods are used to solve the approximate energy when we cannot solve the Schrodinger equation analytically. So there we introduce chapter 8. That mainly accounts for the 2 chapters, because in the Hamiltonian operator, we have the electron-electron repulsion terms, which prevents us to solve the Schrodinger equation analytically. So instead, we have approximation method. Okay. Besides chapter 8, what chapter we're still missing here? 2. Chapter 2 talks about what? Classical wave theory. Okay, and this is something isolated from this class, a little bit. Okay, let's talk about classical mechanics, and we are interested in quantum mechanics. So pretty much, chapter 2 is not quite important. Okay, so if we do not have enough time to review this class, you can skip chapter 2. But if you have time, go over a little bit of your lecture. If you understand all the things in the next class, you will be fine. Okay. So let's go first. Okay, early quantum mechanics in chapter 1. So the first model we talk about is black body radiation. So again, from your slides, you can actually fill in the words here or the phrase. What is a black body? Okay, the definition is it is a physical body that can absorb and emit all radiations to that thing, and regardless of the frequency and the angle of the incidence. Okay, or in one sentence, just absorb everything and emit everything. And we know this is the idealized model we encountered in this class. The first idealized model. Okay. It never exists in reality, but we can have some approximation. As we mentioned in the lecture as well, we have the sun, human bodies, and also this one we talk in class, the light cavity. Okay, it's another black body approximation. So that's why in some early textbooks they use light cavity radiation to represent black body radiation. So that's the same. So first one, you understand the definition. Okay. And then let's talk about black body radiation, the experimental data actually killed the classical mechanics. The Rayleigh-Jeans law and Wien's law, they both cannot feed the data in the whole scope, but only for Planck's law, and you assume energy is quantized. Energy here, n is actually the quantum number, so it equals 1, 2, 3, or it can be 0, and when it's 0 is no energy, so it's no meaning. But say 1, 2, 3. So only by assuming this can you just feed the data perfectly. And I already show you the derivation in the handout. Okay. But you don't need to know the derivation for sure. But here, what can we learn from black body radiation? Energy is quantized. Okay, that's the first thing we introduce you. So next one is the Wien's displacement law. We also talk about it a little bit in the black body radiation part. So Wien's displacement law tells you the relationship between the peak wavelengths with the temperature of the black body. Okay, if you times them together, it gives you one constant. So simply the two factors, the two variables, they are inversely proportional to each other. And remember, the first question you had in this class is asked you to calculate the surface temperature of the sun by giving you the peak wavelengths of the sun. So simply plug into this equation, and you can get the temperature. Okay? Or we can do vice versa. We give you the temperature, we ask you to evaluate the maximum wavelength. Or we ask you to qualitatively compare the different temperatures with different wavelengths and order them. Those are all the possible questions we can get to. But anyway, that's straightforward if you know this relationship. Okay? So next part is the photoelectric effect, right? After the black body radiation. So in this one, we introduced you that based on Einstein's postulates, the light is not made of just electromagnetic waves. Instead, it's made of photons. So something like we have a sun and sunlight, and for quantum mechanics picture, there are lots of photons moving. Okay? And the photon carries energy. And the energy, Einstein postulated that energy of photon depends on the frequency only. So it does not depend on intensity, which classical mechanics believes. So, and also if we can have one equation, that's what we learned in Chem 1B. So energy of the line equals Planck constant times frequency. And based on this equation, actually we can derive something more besides this equation. So E equals HM, right? And we can find a relationship using wavelengths. So how can we express energy using wavelengths? Okay, great. Serial number. A lot more. Use wave number. Remember wave number? HC. Wave number. Okay, and based on this equation, we can tell wave number actually equals 1 over nothing. Okay? So those are the things hopefully you can understand. And if we give you a question related to calculate the energy of the radiation, you know how to do it. Okay? So this is the explanation from Einstein to explain the photoelectric effect. So he believed that the energy can only be transferred between one photon and one electron. So each time the energy transfer just involves two particles only. Okay. And based on this one, also based on the conservation of energy, we can easily derive the photoelectric equation for this phenomenon. Okay. So the kinetic energy of the ejected electron equals the energy of the photon minus what? This is called what? Work function. Good. Work function is not a function. Work function is an energy. Okay. The black body is not always black. Remember that? Black body is not always black. Work function is not a function. It's actually an energy. It's a constant there for a given kind of metal. Okay. So the energy of the photon, if minus the energy the electron consumed by overcoming the work function, that will give you the kinetic energy. Okay. And we know the energy of the photon is h times mu. Okay. And we can actually draw, if we plot Ek versus the wavelength, sorry, the frequency of the light, that will give me this figure. Okay. So the thing is, when I want to ask you, what's the physical meaning for this point? The intersection. So it's a frequency, right? It's a frequency. It's called what frequency? Great. Spectral frequency equals wave function divided by time constant. Remember, I have a homework problem of that. One more question. What does the slope represent? Here's the right answer. H. Time constant. Okay. All the things that you can just explain this as equation. Okay. So that simply means your energy of your photon must be higher than the energy to overcome the threshold frequency in order for you to detect the ejected electron. Okay. And the way for you to increase the energy of the photon is by increasing the frequency of the photon and also decreasing the wavelength. Okay. Decreasing the wavelength, increasing the wave number. Okay. Those sort of things in logic you will be clear about that. Okay. So next one is the Bohr hydrogen model. The RA model for to describe hydrogen, and we have a more formal picture to describe this in chapter 7. But anyway, this is what we learned in chapter 1. We know Bohr's model based on several assumptions. Okay, some key assumptions. The first one is the energy is quantized. And the energy can be calculated using the quantum number and Rydberg's constant. Okay, later we know n here represents the principal quantum number. Okay. The second one is it assumes the angular momentum is quantized. So the magnitude of the angular momentum equals n times h-bar. Okay. The third one is we can calculate the energy transition. Okay. So if we give you a transition, can you calculate the wavelength? Can you calculate the frequency? Can you calculate the energy difference? We're all about this equation. Okay. This is called the Bohr equation, which involves the Rydberg constant. Okay. And for Rydberg constant, for hydrogen, you can just have a solid number here. It's a constant you plug in, and we already practiced a lot for this equation, right? Giving you the spectrum, give you a certain line, ask you to identify n final, n initial, and do some work related to that. So you can check your quiz question and also your homework.
So the first question on the first midterm was about that, and is there any way to know an initial without just being able to identify the series, whether it's like long or Paschen alignment, like mathematically, if we just have to?
You can do it if you can use the ionization line, the last line. So ionization line, n final will be infinity, so that goes to 0, so only left to the NID line, so you can get the series. Okay, so you cannot answer this. This looks like a Bohr series. This looks like a Paschen series. Okay. No, you need to divide it. And final, we'll talk about it. You'll see. So this is actually we'll talk about it. You see the energy level diagrams? We already know the expression for energy, so you can plug in different n numbers. So if you plug in n equals 1 and you convert the energy to electronic voltage, because the first one is negative 30.6 eV. So eV is an energy unit. And the n equals 2, n equals 3, n equals 4, until n equals infinity, that will give you 0. Okay. And for n equals infinity, we call this level as vacuum level. So any energy above vacuum level becomes consecutive, but any energy below vacuum level is quantized. Okay. And here I show a series of transitions here. For the first one with the n final equals 1, this is called what series? Lyman. Good. Okay, Lyman series. And the second one? Bohr series. Third one, Paschen series. Okay. The Lyman series mainly accounts for the IR energy. Okay. If you calculate the energy difference here, the smallest one will give you the IR. It's already falls into the IR region. And this one, Bohr series, first 4 falls into the visible region, and that's why it gives you 4 lines in the spectrum. Okay. And for those UV lights, you cannot detect it at that time. Sorry, I think UV, sorry, UV, visible, IR. Okay. Any questions? And one thing, ionization. The definition for ionization is we promote the electrons directly to above vacuum level. So someone asked me in an email, like, what does ionization mean? Ionization means you completely remove the electron from the particle, or even the molecules. Okay. Ionize it. So it goes to here, and you can actually calculate the ionization energy. But here, you just pay attention, and final must be infinity. Okay. Usually, we'll use this line to determine n initial. And n initial will give you the information about which series. Okay. So as we know, Bohr's model is not perfect. It's far more than perfect. Okay? There's lots of restrictions or drawbacks. The first one is there's no explanation on why orbitals are stable. Right? You say n equals 1, you have the energy there. But why the electron can be there, not by n equals 1.5? No explanation. The second one is unable to explain the emission spectra of other atoms with more than one electrons. Okay. So we define the atom with just one electron as what atom? Hydrogen what? Hydrogen light atom, okay? So Bohr's model cannot explain other spectra from many electron atoms. So this is the second thing. And the third thing is unable to explain the phi structure or even for the hydrogen spectrum. For example, if you carefully examine the red line here, you will see actually it's doubling. But Bohr model never tells you there are two energies for this transition. Right? Only one solid value. So I hope you can now explain this after you learn chapter 6, where we talk about Zemack factor, talk about areas coupling something, solve things together. And hopefully you can explain right now. Okay? So we'll skip this part anyway. But anyway, for those three things, any questions? Okay, if not, next one, the Broglie wavelengths. So the Broglie wavelengths simply believe that matters display both wave-like behavior and particle-like behavior. Okay. And based on this equation, it's simply here, the wavelengths represent the wave-like behavior. Right? Wavelength equals Planck constant over p. P is a linear momentum. So momentum is a particle-like property, also represents the particle-like behavior. So this equation directly tells you the wave-like behavior and particle-like behavior, they are connected here. Okay? And this is one more step. You can express P equals mv. And this is the one I want you to fill in. It's a pretty important one. So it gives you the relationship between linear momentum with the kinetic energy. So you can do it from one step. Okay. I noticed that in the quiz or in the homework, you want to calculate the v first, and then use 1/2 mv squared to calculate ek. You actually did two more steps. Just two steps. So here, if you from here to directly here, it gives you one step. Okay. You know how can we derive that relationship? So why we get this relationship? Okay. For P equals what? MV. For me, okay. ek. Okay, primary physics. And you combine the two. See it? Okay, that's the thing. The one way to do it. Do not solve velocity difference. Okay, just direct it. If we give you P, solve K. Solve EK. Okay, if we give you EK, solve P. Okay, once you get P, you get wavelength. Okay, that's how we do it. Okay? So this is a picture shows you exactly the particle wave duality. Okay, we'll also talk about it in the section. So if you have only a limited number of particles, they tend to behave as particles. But if you have a large number of particles, for example, more than Avogadro numbers of particles, they behave like wave-like behavior. Okay, this is the diffraction or double slit diffraction of electrons. So if you have only limited number, you cannot see the pattern. But if you have many electrons, they show the pattern here. Okay, that's the particle wave duality. All right. Any questions? Okay. Next one on certainty principle. Straightforward. This expression. Right. There are 3 times delta x cannot be 0. So you have a maximum, a minimum number h, or h bar over 2 pi. So again, I want to say whether we use h or h bar over 2 pi depends on the equation sheet we give to you. You always turn to the back page and see which number we give you and use that number. Okay. And this is one cartoon drawn by one of our students. Okay. One thing is missing here is should have a delta. Because we're not talking about the exact value, we're talking about the uncertain amount of the two things. Okay. And this is what we learned actually in chapter 1. But we have a more formal conclusion from chapter 4. You still remember? If the two things, if the two eigenvalues cannot be well defined simultaneously, what conclusion can give you? A and B. You what? They don't commute great. So the commutator is not zero. So this is a more formal conclusion. More formal description for uncertainty principle. So it applies for linear momentum and rotation. It also applies for energy and time. And it applies to A and B, which are not commutative. Okay? So it's a fun time to read it. Alright. Once you know my position, you can know my momentum. Okay. Alright, so that's pretty much for chapter 1. That's pretty much for chapter 1. So before introducing the B part we call inner, I want to put the operators in here. So because operators somehow involve some quantum mechanics here. Okay, the formal quantum mechanics. So first one, what are operators? So operators are a symbol, just symbols to represent some mathematical operation. Okay, when I say mathematical operation, it can be, for example, here taking the derivative. Taking the derivative with respect to x, taking the partial derivative with respect to x, and holding y as a constant. Or you can square it, take the square root. Even for rotate 90 degrees, okay, you can use linear algebra to show the rotation as well. So those are something you will learn in group theory from your advanced inorganic chemistry class. Okay. Even though for rotation, we can also express it in the mathematical language. Okay. So all those things are defined as operators. Okay. And operators, there are some very important operators here. First one, translation operator, and this position operator is the position itself. Okay. Potential energy operator is potential energy itself. Total energy operator is also called Hamiltonian operator, and we use it a lot for our Schrodinger equation. Kinetic energy operator is just part of the Hamiltonian operator, and linear momentum operator, those things. And pretty much for all those things, if we ask you some questions, we'll give you the operators. Okay, so you don't need to worry about memorizing all of them. Like for example, if we give you a question related to this one, we definitely will give you the form of the operator. Okay. Those are the things I hopefully you can understand. And here I want to emphasize something here, one more thing. For this seems like a constant x and b, right? So in our midterm, there's a problem. Question asks you to do. Where's it?
It's right there on the.
It may have something, okay, it may not be the exact one. So this is the operator actually. And the operator you can, I think we're going here. This operator operates on a function. And this is the student's answer. Because he believes that, well, x squared is just a constant. This is the real operation. So I should operate this one on f, not this one. Is that correct?
No.
This is called what operation? Times x squared. Okay, times x squared. Same thing here. This means times x. This means times v. It does not mean constant. Okay. You need to operate on the wave function. So there are several properties for operators. Okay. Hopefully you're already quite clear about that. So operators are not always commutative. So simply means you cannot switch them. Not always switch them. Okay. Not always. If you can switch them, then we say A and B, they commute. Okay, if. And when they commute, we have lots of properties coming up. Okay. Operators are not always associative. So do not do this way. Okay, if you have three operators together doing operation like this way, do not do this one first and then this one. Okay. So instead, you should always do from right to left. Remember, you have A, B, C, D operators together. You always do from the last one to the first one. Okay, so instead you do this way, not this way. Okay, so if you do this way, you can compare the two. They do not always equal the same. Okay, and the last thing, operated on does not mean multiply. Okay, so a operated on fx does not equal to a times fx. You cannot use an operation times a function. What does that mean? Okay. Next one, linear operators. Do you know how to prove linear operators? How to prove that the given operator is a linear operator? You need to operate on a linearly combined wave function. And if you can somehow do the evaluation, you will end up with this expression we call the operator is a linear operator. Okay? Could possibly will give you a question to prove this. And eigenfunction, eigenvalue problems, well, really famous problem in chapter 3. Okay. For ask you to determine whether this wave function is an eigenfunction of this operator. If so, what's the eigenvalue? Well, the way we do is just to set up this. So first you use the operator operate on this wave function, and then use your math to do all the evaluations and see if we can end up with this one. So for this two, if they are the same, if we have identical wave function before and after operation, we call this wave function as what? Eigenfunctions of the operator. And this a, if the a is a constant, we call eigenvalue. So eigenvalues can be a real number, can be an imaginary number, like I, okay, and also can be 0. Don't forget about 0. So 0 times a wave function also eigenvalue. Okay. So any questions right now? Okay, let's go ahead. Commutators, another thing related to operators. For this expression, you know the definition for this expression? Equals what? Negative BA. Any other opinions?
AB minus BA.
AB minus BA. So don't forget about the first part. Okay. So we have already derived that for AB equals negative BA. See that? AB equals negative BA. Okay. So do not change the position. When you run the commutator, if we ask you to evaluate that, do not change the position. If you change the position, you get the negative number. Okay, the negative one we want. Okay, so this is the definition. So as I mentioned again, operators do not always commute, so these things do not always equal 0. So commutators are not always equal to 0. Okay, and if two operators commute, what can we get? If we write commutator equals 0. And we have two important conclusions here. One is uncertainty principle does not apply to this situation. Okay? Simply means if AB, the operator equals 0, the corresponding observables, A and B, they can be well defined simultaneously. Okay, so this violates uncertainty principle. Or simply means uncertainty principle does not apply to this situation. The second one is...
Question, can you repeat that?
So no uncertainty principle means uncertainty principle does not apply to this situation. Does not apply to the two corresponding observables of the two operators here. Okay. So the second one is they have a mutual set of eigenfunctions. So simply means if you find an eigenfunction of operator A, that eigenfunction must be the eigenfunction for B as well, if A, B become it. Okay, so they have the same set of eigenfunctions. So like a mutual friend you have on Facebook. Right? So they have the same friends, but the friend we call eigenfunctions. Okay. All right. So how can we evaluate a commutator? Once we know the commutator equals 0, we have many important things. So how can we evaluate it? So those are the 4 steps you simply need to follow. Okay. The first one is to introduce an arbitrary function. Here I mean arbitrary, it's really arbitrary, just f. Do not say x, do not say x squared, x cubed, something. If you ask me what is the f, I don't know, it's just a function. It's a function of x. Okay, I just put here. And the second one is expand the commutator using definition. We already know AB operates on f minus BA operates on f. And the third one is your math. Hopefully you can go over and go through all the calculations and you end up with this expression. maybe an operator, maybe a constant here. Okay, depends. So it's an operator. If this operator is say operator C operator on F, if the constant is C times F, and then the last step is to take off F. Okay, kick it up, and you get this one. And that's what we are looking for. Okay, and if you find this one is 0, great, they commute. If not 0, they do not commute. Okay, any questions? Very important, again, very important. Okay, make sure you know how to evaluate commutator. So next part, Hermitian operator. This is the definition. So if you understand the definition, that's enough. Okay, that's enough. We will not ask you to prove this is the Hermitian operator or not. Okay? We'll just test you some understanding of this. So basically, this is less likely for us to make you questions, but the followings are pretty easy to make questions. So there are some characteristics of the Hermitian operators. The first one is the eigenvalues must be real. Okay, eigenvalues must be real. That's why for most quantum mechanics operators, they are Hermitian operators, because their eigenvalues are either like total energy, potential energy, kinetic energy, position, momentum. They are all real things. Okay, so the eigenvalue must be real. So A equals A star. The second one is you have different eigenfunctions of the same Hermitian operator. They must be orthogonal. So they must be orthogonal. So here I bring up this concept. Orthogonal here simply means if you do this integral and make sure your A and M are not the same, they give you 0. Okay, this is called orthogonal. And remember in chapter 4, once we talk about orthogonal, we'll talk about another concept right after orthogonal, that is orthonormal. So orthonormal is if you have normalized the situation, we'll talk about normalization later, okay? If this one is normalized, and also this two, they are orthogonal, we call that orthonormal. Okay. For orthonormal, how can you prove it? You can also do this setup. You integral the two wave functions, one is complex conjugate, another one is the self. Integral it within the whole space, and that will give you the Kronecker delta. You still remember the physical meaning of Kronecker delta equals something, two situations there. Okay, let's say if n equals m, then it's 1. If m is not equal to n, okay, that's the thing. So equals 1 corresponds to normalization. Equals 0 corresponds to orthogonal. Okay, or orthogonality. Okay, so that's how you prove orthonormal. Okay. And then we'll go to the chapter 4, so formal postulates. So have a formal description. Okay. This is the first one, postulate number 1. So unfortunately, postulate number 1 is the longest one. It has 4 layers of it. The first one is it talks about the statistic meaning of wave function. Okay, so we'll review again. For wave function itself, just describe the state. No physical meaning. So if you ask me what is the physical meaning of just a wave function inside there, well, I don't know. But we can define probability using wave function. Do you still remember the definition for probability density? Right, dp over d tau is simply the probability density equals the complex conjugate times wave function itself. And I heard someone say square, better to say magnitude squared. Because we already proved that, I don't know whether you still remember. Magnitude squared is not always equals to squared, like this. Okay. This happens if the wave function contains the imaginary part. Is that different? I already showed you in the handout. Okay. So you can write magnitude squared, that's okay, but do not write square. Okay. And we have probability density now, so we can define probability of finding something in a finite space. Okay. Simply you just move d tau to the right hand side. And that's your probability. That's a statistical meaning of wave function. Okay, so wave function, how can I understand it? We try to understand it in a statistical way. So it's based on something, the probability. So that's also why for the following chapters we talk about a lot of probability. We say quantum mechanics is just a set of probabilities. Okay, so you cannot imagine, you cannot predict what questions we will give to you on Monday. Okay, that's uncertain. Okay. But you can predict probability. The second one, we're still in postulate number one. Okay, we're still in number one. The second meaning, second thing talks about normalization. So to do the normalization, why would you normalize a wave function? It's simply because the probability of finding that particle within the all space must be 1. It must give you the probability of 100%. So there are two different setups. Okay, two different setups. For in Cartesian coordinates, where you already know, it's just dx divided z to represent your volumetric volume. So here, I talk about 3-dimensional one. So for 2-dimensional, just dx divided, 1 dimension is dx. Right? N dimension dx divided is z until the end. Okay? But anyway, this is straightforward. I believe everybody can set up the equation right now. But in spherical coordinates, it's a little bit different. Can you write it down? Can you write it down before I show it to you? So where's the trick? Where's the trick for spherical coordinates? Okay, in the volumetric unit. Right? Instead of dr d theta dphi, now becomes r squared sine theta dr d theta dphi. Can you write it down? Alright? But here we're doing the 3 integrals here. For a specific case, we need an integral with respect to r, with respect to theta, with respect to phi. So we need to know the bounds. Right? What's the bounds for r? What to infinity? 0 to infinity. And can be 0. Okay. What's the bounds for theta? 0 and pi. What's the bound for phi? 0 to pi. Great. Okay. So those are two things. The thing you need to know. You need to put the bounds here to do the evaluation. Okay. But also again, I want to emphasize here, don't forget about this. Okay? Especially you have limited time in your final. If you mess up here, your calculation will completely be messed up. You will spend hundreds of times to redo the integral. Probably you will end up with something, well, I cannot find the standard integral. What happened? Okay? That's happening here. Okay? Postulate number 1, normalization. Here we talk about the step to normalize the function. Okay? It's just a pretty brief review. I believe most of you are quite good at normalization now. So we need to put a constant before the function. That constant is called normalization constant. And then we set up the equation using the definition of probability. But here we integrate over all space. So here is a magnitude squared. Okay, so I put magnitude in case this is a complex number. Okay, if this is a real number, it's a squared. Okay. And step 3, evaluate the bound equation. Also, you need to use your calculus, or you need the standard integrals. You can work it out and set this one equals 1, right? And you can solve A. So once you get A, there are two situations for you to tell. The first one is if A equals 1, the given wave function here, fx, is already, or phi x is already normalized. So you don't need to worry about normalizing anymore. They are normalized. But if A is not 1, let's say equals B, a constant B, so then the wave function, original wave function, is not normalized. And if we ask you to find the normalization constant, easy, just B. It could be there, normalization constant. And better to write another word, another sentence. So the normalized wave function is here. Okay, that's what it's saying you need to do. So hopefully everybody will know how to do the normalization. Okay, this is super important. Okay. And we're still in postulate number 1. The third thing I'll talk about is probability evaluation. And you can see the first row talks about normalization, and the second row talks about probability. So the only difference is the bounds is different. Okay. To normalize the wave function, you integrate over all space. But to find the normalization with a finite volume, you only integrate over the given space here. So here I use a 1-dimension situation here. Okay. So those are the things that are different. Okay. But again, when you do the probability, the first question you need to ask yourself is whether the wave function is normalized. Okay. We can give you a tricky question. The first one, instead of asking normalize the wave function, we ask you please find the probability between A and 2A. Okay, if you do not normalize it, you use the unnormalized wave function, you probably get a probability larger than 1. Okay, so that's the thing. Keep in mind, don't forget about normalization. Okay. Fourth one, we're still in postulate number 1. Talks about requirements for well-behaved function. Okay, so what are well-behaved functions? The first one is they should be continuous. This is because you want to put the wave function into the Schrodinger equation, and all the Schrodinger equations that talk about derivatives. So you want to make sure your wave function can be derivative. So it's called continuous. So from your math, in order to be derived by something, you need to be, the wave function must be continuous. Okay. The second one is must be single value. So at the same position, right, think about the physical meaning of the wave function, the statistical meaning. It talks about probability. So for a given wave function at a given position at a given time, there's only one probability. You cannot have double probability, two probabilities. So what does that mean? So this is a single value requirement. So in order to be well behaved. The third one is must be finite everywhere. This is because of the normalization here. So based on number 3, we divide 3.5, another byproduct. So to rephrase finite everywhere is to say quadratically integratable everywhere. Okay, this is because of normalization here. We know if the wave function is a real function, it's actually square. So if the square of the wave function must be integrable here. Okay, this integral must be finite. So it cannot give you an infinity probability, right, to find the thing. That does not make sense. Okay, and those are the things for postulate number 1. Okay, so we can make a summary here. For postulate number 1, we talked about 4 things, right? The first one is the statistical meaning of wave function. The second thing is the normalization. Third thing is to calculate the average value. Fourth thing is the requirements for a well-behaved function. Okay, fourth thing is 4 in 1. That's postulate number 1. It's a pretty long postulate. And postulate number 2 is straightforward. It talks about a correspondence. A correspondence between classical mechanics, classical observables with quantum mechanics operators. And they are linear and Hermitian. Okay, they are linear and Hermitian. And again, the question, what's the property of the eigenfunction of a Hermitian operator? What's the characteristic of the eigenvalue for a Hermitian operator?
Real.
It must be great. It must be real. So all those observables must be real, right? And have an imaginary energy. Okay. Number 3 talks about eigenfunction, eigenvalue. Also straightforward. So it says if we have a state composed of several subsets here, okay, eigenfunctions, and they correspond to different eigenvalues, and you do the measurement. Every time you do the measurement, we'll just give you one case. Okay, it's like a roll the die we give you in the lecture. We have 6 probabilities, but each time you roll the die, you get just one. Okay? That's sort of the idea of superposition. You think about it. Everywhere probability, but if you do the measurement, the superposition collapses to one state. That's postulate number 3. Okay. Postulate number 4 talks about average value, standard deviation. Okay. And we'll show you lots of equations here. But again, I want to ask the question, before we do those calculations, what we should do first? Normalize first. Okay. So once you normalize it, the average value, well, some textbooks, they use the expectation value, but in our class, we always use the average value. Is this, right? So if we talk about average energy, you just change the operator here to a Hamiltonian operator. If it talks about average position, you change the operator to the position operator. Okay, those are something you sandwich the operator in between the 2 wave functions and do the integral. for all space, okay, of course, for all space. That gives you average value. Okay. And this one is once you find the average of A squared and the average of A but square it, okay, these two are different, okay, the two are different. And you find the difference, that will give the variance here. And once you get this guy, you can get standard deviation simply by taking square root and choose the positive one, and that's the standard deviation one. Okay? And you will see this too actually based on the calculation of average value. Okay? By the way, how can we evaluate A squared average? So you square the operator here. Okay? And when you do the evaluation here, don't forget the operator operates on the wave function here is one identity. So you need to do the evaluation here first, and then do this one, and then do the integral. Okay? Do not do from this way. Okay? Do not do from left to right. Always from right to left. Okay? Postulate number 5, time-dependent Schrodinger equation, beyond the scope of this class. Okay? If you are interested in that, you can choose advanced quantum class. We will talk about it. Okay. Those are the 5 postulates in chapter 4, but they are not the complete set of postulates. We're still missing one. That's postulate number 6 in chapter 9. When we talk about the electronic wave function, here I want you to fill in here. It does not talk about the harmonic oscillator wave function or radio rotator wave function. Instead, we ask you to talk about the electronic wave function. They are anti-symmetry. And you still remember the meaning of anti-symmetry? Oh, anyway, that's like that, right? You change the position. Let's say you have 2 electrons. You change the position. You change the sign. And you can easily prove it by using the Slater determinant. Okay, and using linear algebra. You will see once you change the position, you end up with a different sign. Yeah, so this property is called anti-symmetry. And postulate number 6 just requires all the electronic wave function to be anti-symmetric because we want to obey Pauli exclusion principle. Okay, that's the thing. And we're already proving that in the section, so you can go back to the next slide for detailed derivation. But here, just be clear about the concept. Okay? So
a Slater determinant is just a normalized wave function that's been
yeah, it's just a wave function. Shorter way to do it because it's actually the real way is like this. Remember the algebra way like that. Here we use the linear algebra way to shorten the wave function, but still a wave function. Okay, Slater determinant is called the determinantal wave function. It's a wave function. So any questions about the postulates? Okay, postulates are very important for the following chapters by using again and again those conclusions we use in chapter 4. Okay, so if not, before going to the following chapters, there's one thing behind the superposition, okay, which is just the end part of chapter 4. And I believe you already, you still remember the 2 examples we gave you in the section. It's everywhere. Georgia's cat, or you can imagine around the campus, that example. Okay. So the general idea is this expression. And the expression here, the left-hand side is a superposed wave function. Or you can try to think about that, so total wave function. And all those coefficient here is called the Fourier coefficient. The Fourier coefficient times basis wave function. Okay, and you can, this is the summation way, and you can expand it like this. So simply means the superposed state is composed of different basis states with different, here C, related to probability. Okay, and we can ask you to normalize the superposed wave function, find probability, find average value. I still do it. And you still remember, in order to normalize the wave function, there are 2 ways to do it. One we call Gates method, one's called my method. My method is to derive the normalized coefficient, right? To derive normalized coefficient and then put change the position of coefficient for each one. Or you can use Gates method, just put an n here, and do the normalization as if you are doing the single wave function there, and you will still be able to get the value. Okay. You can check the homework from us. We'll give you the key. Right? We have two set of methods, and choose the one you feel the most comfortable. Okay. So usually I would read this question because I know the two methods. Okay. Sometimes the game is not quite familiar with my method, so I will always be the one grade those type of questions. Okay. So be free to use any method you want to use. Okay. I can understand why you are doing this. Okay. And probability, well, still after normalization, you're finding the probability. You still remember they say the probability for this state to be in this state is what? The square Fourier coefficient, and we're going to say normalized coefficient. So normalized coefficient. If it's not normalized, do not use it.
So one issue I had with finding the normalization constant was for the bottom part of the denominator. It wasn't clear as to whether you're supposed to square all of the other Fourier coefficients after they've been added together, or before?
Before. So here, C1 squared, C2 squared, C3 squared. Okay, do not use normalized. Just use the original. So the question asks, what C should we put in here? Should we put it normalized or not? We should put the original.
No. The question is, do you square it before or after the sum of all of the?
Oh, square before the sum. Okay, square before the C1 squared plus C2 squared plus C3 squared. So square them first and then add them together. Okay? And average value, you write it down. Average value. My average value of A is the probability of A state, the one state times the eigenvalue of A1, plus the second one, say square, A2, say 3 square, A3. Usually will be a follow-up question after normalization and probability. Giving you the eigenvalue for this state are A1, A2, A3, find the normal, find the average value. Oh, doable. Doable. Okay. So any questions? All right. So now we go to the really huge part, so energy. As we know, when we talk about microscopic system in this quarter, I mentioned again and again, we're mainly interested in two things. Okay? One is energy states, another one are wave functions. Okay? If you understand energy and wave function, you pretty much understand most part of the microscopic system. Okay? So here, instead of going from one chapter by one chapter, I will summarize all the energies from different chapters together. And after that, I will summarize all wave functions from different chapters together. And hopefully you can follow me and don't get lost. Okay? Okay, let's start. The first one is when doing the energy for wave function, we need to know the Schrodinger equation. And this is the general structure for Schrodinger equation. Schrodinger equation is composed of a Hamiltonian operator, and the Hamiltonian operator is composed of two things: kinetic energy operator, potential energy operator, both up here and here. And they operate on the wave function equals, this is called what energy? Total energy. Okay, the eigenvalue for Hamiltonian operator is total energy equals E times or operator. E times wave function. Okay, E times wave function. And first one, particle box system. Okay, in order to derive the energy, we need to know the Hamiltonian operator. And in the Hamiltonian operator, we have potential energy operator. Okay, so we need to know the potential energy distribution for this particle in the box picture. So again, just a review. For particle in the box, pretty simple. Within the box, you know potential energy. Outside of the box, including the two boundaries, the potential energy is infinity. Okay, it's infinite high walls on the two sides. Okay, and they combine with electrons. Okay, that's the thing. So based on this, you can set up your Schrodinger equation. And actually you can afterwards analytically solve the Schrodinger equation. So I will not show the derivation here. Okay, just go back and solve, and you get this equation. This energy related to n squared, and is a quantum number. Okay, and also you can evaluate the energy transition between two different energy states. So n final and n initial. And also you can draw the energy diagrams using this equation by plugging n equals different numbers, and you will naturally find the gap between adjacent two energy states increases with increasing quantum number. Okay, we will do a summary later, okay, for talking about the characteristics of the energy gap. And here the first, actually the second example, okay, the energy gap increases with increasing quantum number. Okay. And quantized energy, the energy is also quantized for 5 megawatts. For n-dimensional, the general expression is to sum all energies together. Okay, if you have the energy from the first dimension and the energy from the second dimension, simply add them together. And for the specific case, for 3-dimensional world, you have the 3 terms add up together, and when A equals B equals C, they go to QB box, and you have this, simplified version. Okay, and based on this one, we talk about degeneration, degenerate and degeneracy. So several different states with different quantum numbers here, if they have the same energy, we call those states they degenerate. And the number of those degenerate states equals degeneracy. Okay. Yeah, you can write down those things beside this one. Okay. I want you to make your own review slides. And you do not follow exactly my pattern here. Okay. You can write whatever you think is important beside those things, or in the blank area. Okay. So those are, the previous one is chapter 3. Okay. So now from chapter 3 to chapter 4, 4 is postulates already talked about. So go to chapter 5. Chapter 5 is harmonic oscillator. And the energies are also quantized. So here, the quantized because we have a vibrational quantum number here. Okay. And this frequency you can expand using wave number here. So from chapter 5, instead of using the nu tilde here, we use omega tilde as a wave number. So somehow they change the notation, but the physical meaning is the same. Okay. And based on the equation here, the one in blue is called the fundamental vibrational frequency, and this is a very important one, right? We can give you lots of questions asking you to do some work related to this, simply because the fundamental vibrational frequency contains here force constant. Okay, force constant. Force constant, something related to bound order. So here's a connection between chapter 5 and chapter 11. Okay, we give you something and incorporate them together. Where's the joint point? Here is the joint point. Okay. And other things I really expand here. And let's see the energy diagrams based on the previous equation. You will see the energy gap here, they are always equal no matter what quantum number you have. Okay? And they always equals h nu. So that means if you have the theoretical spectroscopy, the vibrational spectroscopy, the energy transition will always give you one wave number, so you only have one line. Okay, remember I have a question? Ask you to choose. Okay, let's see the correct answer. And another thing is, when n equals 0, you can get the energy is not 0. So we call it the non-zero energy. So again, 0 energy for a harmonic oscillator is not 0. Okay. Instead it's 1/2 h nu. And based on 0 point energy, from your midterms, we already talked about that. It's actually the direct result of uncertainty principle. Okay, this is how you prove it. Okay, do I need to go over it? It's sort of like if you express 0 point energy, it is related to the average value of t squared, average value of x squared. But if you let this one equals 0, the 2 must be 0. But once the 2 equals 0, uncertainty here will be 0. That violates the uncertainty principle. So that's the general idea, right? If you feel rusty about this, make sure you go back and review your midterm question. Okay, there we talked about this. So across chapter 5 to chapter 6. Okay, chapter 6, rate rotator. Energy is again quantized. this quantization here is caused by this quantum number. It's called rotational quantum number. And pay attention here, J equals 0. The same thing for vibrational quantum number, n from 0. Okay. But the quantum number for particle in a box, the minimum one should be the minimum quantum number for particle in a box. The one is not 0. Okay. So, but for harmonic oscillator and ridge rotator, they are 1. They are 0. So they are 0. Okay. So here B is the rotational constant, okay, related to, okay, I did not express here, following chapters, following slides here. So B tilde actually is related to the bond length, okay, bond length. And again, bond length, another joint point, where we can talk about the bond length in chapter 11, remember? There's the figure there, the distribution, the potential distribution, and we have the minimum point. There, the bond length, okay. And again, we can join them together. J equals 0, 1, 2, the quantum numbers. And degeneracy, okay, degeneracy for a state with quantum number J is 2J plus 1. Okay, this is pretty much a conclusion you need to just memorize it. Okay. And let's see the energy transition, the diagram. So the key feature here, first thing is the 0 point energy is 0. So if you plug in J equals 0, the 0 point energy is 0. It's unlike harmonic oscillator. Okay. And about transition here, actually the energy gap, again here energy gap between two adjacent energy states increases with increasing quantum number. Okay. The 2B, 4B, 6B, AB. And interestingly, the difference between the two energy gaps, which are here, which are represented by delta E, is always 2B. Okay, so although the energy difference is increasing by 2B, but the amount of increased amount is always 2B for each state. Okay, hopefully still remember this, and this will lead to the pattern of the rotational spectroscopy, where you have equally spaced lines. And the absolute wavelength for each peak here is 2B times J plus 1. So it's 2B, 4B, 6B, 8B. But the space between two adjacent lines is always 2B. Okay. And remember some similar question we can ask you is some questions like, oh, given the space between the two adjacent lines, blah, 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 some wavelengths, right? Please evaluate bond length. Remember? How can you evaluate that? Because you know the space here equals 2B, so you can get B, and from B, you can get bond length. Okay, that's the way you do it. And this is a vibrational rotational spectroscopy. So lots of things here. I do not have time to go over in detail. But here, this picture shows most of the features here. Okay. B branch, O branch, and R branch, their wave numbers. Okay. This is by assuming they are just like behave like a radio rotator. Okay. For a more complicated situation, like in the quiz, we ask you if this behaves anharmonic oscillator or is not a rigid rotator. It's not a rigid rotator. They account for the different uneven space here, and we ask you to expand at that time. Okay. So here one question. So what causes the missing line in the middle? What causes the missing line in the middle? Because we don't want the right equal 0. That's related to selection. Right? Selection. Okay. Delta J cannot be there. Delta cannot be there. Hey, delta J cannot be 0 there. Yeah, delta J cannot be 0. Okay, vibrational spectroscopy and rotational spectroscopy, they have different applications, right? For vibrational spectroscopy, what we can get is the force constant. This is because the vibrational frequency can have there contains the T value.
In the selection rules, delta J can be 0, but you can't transition from 0 to 0.
0 to 0, yeah. So yeah, remember that delta J equals 0 cannot go from J equals 0 to J equals 0. Okay. That's like back when I remember something related to the selection. So back here, vibrational spectroscopy, it talks about force constant. Okay. You can get force constant. Like if you do IR, we have a question in the homework, right? You do IR, you can evaluate K values. And rotational spectroscopy can give you a bounded. That's due to the 2B, the space. Okay, from B, you do the moment inertia here, you can get the wavelength. Sorry, the boundedness from the rotational spectroscopy. Okay. And here, the thing I skipped in the selection rules for vibrational transitions and rotational transitions. Okay, I did not cover here. I cannot cover everything today, but as was mentioned here, you can write down the two things besides here and go back and check those things, especially related to dipole moment. Okay. Okay, across 6, we go to 7. 7 is hydrogen atoms. Hydrogen atoms. And this picture I already showed you, so it's based on actually the Bohr model, where it tells you the energy related to n squared. And the quantum number, there's no principal quantum number. So you can construct the different levels like in this way. And again, you will find the energy gaps between two adjacent inner states actually decreases with increasing quantum numbers. Okay. We already see many patterns here, so this is the third pattern. And we talk about in this chapter, for different situations, you have different energies. So the previous energy actually is the unperturbed energy. So it's the original one. When you do not consider any effect, the energy of the hydrogen atom is this. But let's say after considering about LS coupling, the orbital and the spin angular momentum, they couple together, they interact, it will give you some, here, sorry, I think I put a wrong equation, sorry. Should not have these two terms here. So only about the group terms. So that will give you the perturbation. Okay, the perturbation here a little bit, and change the energy a little bit. Okay. You can just cross out this part. I think I placed the wrong slides here. So only with perturbation here. So perturbation here is just a small value that slightly modifies the value here. It slightly modifies the value. Okay. Question? So this is actually the picture of the energy splitting. Okay, this is actually a popular topic in chapter 7. But given lots of different situations, I ask you to draw the energy level diagram. Okay. The left one is the unperturbed situation. And we learned for one s orbital and 2p orbital, we only have one line. But this actually is not the real picture. That's why the Bohr model, they failed to explain some fine structures here. Okay. So instead, you need to consider about LS coupling, and the energy state actually split. And you'll see this one split into 2, this one split into 1, and I already will use term symbols to represent them. So we already divided in a section. Okay. The number of split energy in this case equals the number of what quantum number? If you just consider LS coupling. Okay, I heard the right answer. Yeah, Jay. Okay, but before that, one more thing I want to say is degeneracy. Okay, degeneracy for each state here equals 2J plus 1. It's actually the same thing as what we're talking in radio rotator. Okay, the same thing. Okay. And the next thing is number of split inner states equals number of J. Okay, for example, here, the s orbital, later we'll talk about term symbol. Right now, I hope you can do it. You will see this J value only one value. So only one value is only split into 1. Okay. This P state has 2 values, so split into 2. Okay. Oh, this is actually the real, the correct slide. So that previous slide should not have this 2, but now should have this 2. Okay. So this is called Z-band effect. So based on the LS coupling law, if you apply the weak external magnetic field, you will also perturb this atom, and you will have 2 more terms here related to different things. Here is related to the orbital angular momentum interaction between orbital angular momentum with the magnetic field. This one is the spin angular momentum interact with magnetic field.
Should we memorize that?
No. No. If we ask you to write down the Hamiltonian operator or like Schrodinger equation, we definitely will give you this unit, okay, the block you need to use. And user perturbation theory, we didn't talk about that anyway, so you don't care. So we will give you another terms that related to the changing energy. Okay, the changing energy. And again, you don't need to memorize this equation. We will give you. Okay, we will give you like the homework program. This is the picture actually more important than the previous equations. Okay, so if you only apply the weak magnetic field, the energy will also split. And in this case, the number of split energy states equals the number of what? Quantum number. The what? The what? In this case, if just magnetic field, no LS coupling.
Just the number of
Great, ML. Okay, ML. So also you can find this one has 3 ML values because P orbital L equals 1. Right, ML equals 0 plus minus 1. 3 states, here 1 state. Okay. A more complicated is you, after considering LS coupling, you already split according to J. And now we apply the magnetic field. So in this case, the state will be further split, and the question is the number of split energy equals the number of what quantum number? Number of MJ. Okay, MJ. You can find like this one, J equals 4 values, 2 values, 2 values. Okay. Alright, so those are things you need to memorize. Okay. We can give you some questions like with different situations, draw the figures. It's doable. It's doable. But that's something related to also quantum numbers, or the term symbols. We will talk at last. Okay. Okay. Chapter 7. This is chapter 9. Or chapter 10 actually. Well, chapter 9, many electron atoms, we did not talk about the energy. Okay, so we directly go to the molecule. So for the molecule, we talked about the energies for bonding orbitals and anti-bonding orbitals. And these are the 2 equations we showed you. Okay, so for these 2 expressions, we have the 3 integrals and the ON meanings. And especially important thing is the overlap integral. It talks about how the 2 atomic orbitals, or how those atomic orbitals overlap with each other and form the chemical bond. Okay, we have already talked about this in this week, so hopefully your impression is still fresh for this part. Okay. And this is the energy diagram of the ground state hydrogen plus molecule. Okay, hydrogen molecular ion. And again, that's what I mentioned here. You have a minimum point, and you can find the distance here for this minimum point. And that's exactly the thing we call boundness. Okay. And from here, you will see we can give you some questions related to radial And here we connect the 2 chapters together. Okay. So that pretty much will be the style of final exam. Okay. We'll not give you a question, just simply emphasize on that part. We will give you something incorporated with each other. Okay. Also things they mix together. Any question about reading this figure? Highly important. Okay. So you understand all concepts here. Okay, chapter 11, Parker model. Okay, we talk about conjugating molecules. And this is the energy state where you can get after solving the Parker determinant. Okay, Parker determinant. By using this relationship. And remember, here beta is what? Beta is negative. So after this one will be the lowest one. This one will be the highest one. So when you record those high electronic energy levels, always do like this way. Okay, use your 1 to represent the ground state, and the maximum number to represent the most excited state. Okay, by doing this way. Okay, after you construct the energy levels, you can draw this energy diagram and fill in the pi electrons. For example, here, butadiene has 4 pi electrons, and you fill in this way. Okay, and you can evaluate the energy for this case. We call the delocalized situation. That will be this one, right? And also we have the localized situation, where you think this butadiene are just composed of 2 ethylene molecules. And you know that for each one ethylene molecule, the inner state is like this. And for each one ethylene molecule has 2 pi electrons, so I fill in the electron states. I can also evaluate the energy here. And from here, we define the localization energy as the difference between the localized situation with the sorry, the delocalized situation with the localized situation, right? And in this case, the difference will be this, and it will be a negative value.
When you have 4 pi electrons and you're solving your secular determinant, and then you get x, and then you have that, will you always get 4 different values if you have 4 pi electrons?
That depends. You're talking about degenerating. Okay. Sometimes you will have the several states have the same energy. So sometimes you get 4 different values. Sometimes you maybe get just 2 different values. With like alpha, alpha, alpha.
Well, I'm talking about right here, like you got plus or minus 1.618, and you got.
You mean here?
Yeah, that guy.
Yeah, you can also get if this energy state degenerate. If degenerate, you can have one more with the same energy. It's possible. Okay, and it only applies for cyclic molecule and star-shaped molecule. Remember that? For this one, it's neither one, no degeneration, no degeneracy. So it's always at different values. Okay. So anyway, this one delocalized energy. Okay, usually is negative. So once when we ask you to find delocalization energy, you get a positive value. 90% like you did it not correct. Okay, if you go back, check the evaluation. Okay. So now, as the last of the energy parts, we want to make a summary. And I hope now you can help me to fill in this table. Okay. From the first case, what microscopic system can you think of? Yeah, think about chapter 3, from chapter 3, particle of box. Particle of box?
Yeah.
Okay. Besides particle of box, we have one more. No, particle. What? And harmonic oscillator? No. Raging rotator. Okay. The second one. Okay, the second one. So one more thing. Particle box corresponds to translational energy states. Okay, we didn't mention that, but here, in order to form a complete picture of this talks about translations. Okay. But the energy gaps remain the same. Harmonic oscillator and just harmonic oscillator. And the final case, the last case, hydrogen atom good and what? And harmonic oscillator great, yeah, it would be great. Okay, so those are pretty much the same. Okay, now we'll talk about energy gaps. For like molecules, many electron atoms, we don't talk about that. Okay. All right. So this actually anharmonic oscillator applies to molecules. It applies to molecules belongs to this case. It's an anharmonic oscillator. All right. So any questions? If
The anharmonic oscillator is just a more accurate harmonic oscillator, right?
yes. Okay. It's considered about it's not always a harmonic oscillation. Okay. We finished a huge part, and there comes the last huge part, the wave functions. And again, let's take it back to chapter 3 and move to chapter 11. Particle in a box, wave function, normalized one is like sine function. Okay, sine function. And here we define the thing called node. For a node is where the wave function is 0, or you can say the probability density is 0. Okay. Remember I have quiz questions? Ask you to identify the position of the nodes. Right? Those things. How can you do it? Set the wave function to 0, and you can find it. Okay. And we actually specifically we derive a relationship here for a particle in a box is the number of nodes with the quantum number. Right? For example, n equals 1, how many nodes? 0. No, not 2, okay? Not including the 2 boundaries. For the n equals 1 case, well, no, number of nodes.
1.
Where is that?
Middle.
N equals 3?
2.
What's the relationship between n and the node number? Okay. We have a question in midterm, second one. Remember? Show your picture. Give us a normalized wave function. Okay. And the wave function in general, n dimensions, is you find the wave function from each dimension and times them together. Okay. And for a specific case, three-dimensional one is just like this. And again, for cubic box, A equals B equals C, we reduce to this expression. Okay, make sense? All right. Chapter 5, the wave function of harmonic oscillator is somewhat kind of complicated. So we do not require you to remember it. So instead, if we ask you to prove orthogonal or normalization somehow, we will give you the wave function. So the only thing you need to know is the one in chapter 4. How can you set up the expression for normalization, and how can you set up the expression for orthogonal? Okay? We do the same thing here.
Could you repeat that? Could you just say?
You just need to know how to set up the normalization, how to set up the proving the when the two are orthogonal. Right?
Evaluate?
Yes. And from the evaluation, we talked about odd even function. Remember odd even function. Okay, so here you can just put out reflection here. Odd even function part. So for odd function, if we integral over a symmetric space, okay, first case, first condition, symmetric case, I have odd function. What we will get? If a symmetric space about an even function, what we get? 1, 0.
It would be equal to the interval from 0 to A, but times 2.
Yes. Okay, you can reduce to half. Okay, reduce to half. Okay. And how will this give you what? 0 to A for an odd function. Equals what? Negative. Right, you do change the value. Okay, those things are from your map. Okay. And possibly you will see actually this wave function, they are either odd or even. So we can simply give you an even function, ask you to normalize it, and it will give this case. Okay. So here it's talking about the boundary conditions. Here I put the line here, the two circles. So those are not boundaries. Okay, because for boundaries, wave function must go to 0. But here is not 0. So instead, what are the boundaries for harmonic oscillator? So go to infinity, okay, not something here. Okay. And also, when we ask you to normalize something, the wave functions using the harmonic oscillator, that's for two bounds. Okay. Radial rotator again. It's quite complicated, and we will definitely give you the exact form of the wave function we want you to use. So you don't need to worry about those things. But you need to know how to set up the normalization, and how can you set up the expression to prove the two are orthogonal. Chapter 7, hydrogen atoms, is based on the radial rotator. We're going to introduce the harmonic oscillator here, the spherical harmonics, but with one more thing is the radial parts. Okay, so this is called angular parts, this is called radial parts, and the two, you tie them together, that will give you a complete wave function for hydrogen atom. And still remember from this picture what important conclusion we derived. The number of radial nodes equals n minus L minus 1. Okay, n minus L minus 1. This, for example, 2p. For 2p orbital, n equals what? 2. L equals 1. 2 minus 1 minus 1. Okay? Oh, sorry, yeah, 0. 0 nodes here, but 1 maximum. Okay, 1 maximum. Nodes is represented by both nodes. Okay? And this one, we divide the number of angular nodes equals L. Equals L. Okay. And so we can give you a question like this. Right? Identify what orbital this is. Okay. How many radio nodes? 1, 2. So n minus L minus 1 equals 2. Right? How many angular nodes? So this is 4p. Okay. And again, in a two-dimensional picture here, all the radio nodes, they are circles and circles. Okay. For angular nodes, that's straight lines. If you have a question, you have a homework question, you can just go back, check it out. Okay. Again, this is a popular question in this chapter. Okay. Any question about this? Make sure you fully understand it. Okay. Chapter 9, many electron atoms, the wave function is expressed as Slater determinant. And this is the structure of Slater determinant. Okay. It's straightforward to write actually. So if you understand the structure. So here is the normalization constant. Okay. And for each one here, the first one represents the orbital. So it's a spatial wave function. So it's orbital 1s, or this first one anyway. And here alpha is called spin wave function. So they are wave functions. The alpha means spin down, beta means spin up. So alpha means spin up, beta means spin down. And that one simply means the electron 1 is in this orbital. Okay, this orbital is described by the first psi 1 and spin up orbital here. So it's inside of this. Okay. And once you get the first element, you will know for each row they represent the same orbital, but only change the electron. So once you know this guy, you know this guy, but the only way you need to assert here, same electron, different orbitals. So you know this is n electron, so you get like that. And for each column here, representing the same orbital. So it's either, if you figure out this one, you can copy here, copy here, copy here. The only way you need to change is to change the number of electrons. Okay? And based on that, you can set up the things.
Which is the second wave psi 2, not psi 1?
Psi, where's psi 2?
Like psi 1, the second.
Oh, no. This is psi 1 alpha, that's one orbital, psi 1 alpha. And this is psi 1 beta, the beta stays. Psi 2 is here, psi 2. Psi 2. Okay.
You do that when it's twice as wide as it is.
Not twice as wide, it should be n by n here. Should be a cube thing. So here it is because here is wider than the space here, so it looks like twice as wide.
So you have psi 1 to psi n as n, and you have psi 1 to beta.
1 to n is still n.
You get it n down to 2 n.
No, just n. So one. So this one. Oh yeah, a little bit. Yeah. But sometimes this cannot be completely filled here. So it should always be n times n. Always be n times. There should be a cube configuration. This is a little bit tricky here. This is a general.
You just keep doing wave function times alpha, beta, alpha.
Yeah, alpha, beta, alpha, beta.
It doesn't have to end on beta.
Yeah, it does not.
How would you set up the determinant if you were going to do it of a diatomic molecule?
The atomic molecule is, you change the notation here a little bit. So here instead of phase 1, maybe the psi 1, like sigma. 1 sigma, 1 sigma, 1 sigma G, 1 sigma U. That one. You just need to change the notation. But you have the molecular orbital here. Right? You construct that as the type. Right? Chapter 10 and 11, molecules, the wave function is composed of the one we call LCAO, stands for linear combination of atomic orbitals. Okay? So this is actually a superposed wave function. So the superposed wave function is actually the molecular wave function, and all of those basis wave functions are atomic wave functions. So linear combination simply means you times coefficient and plus them together. Okay? And one more conclusion from here is the number of molecular orbitals must be the same as the number of atomic orbitals you choose to linearly combine. Okay, to linearly combine forming the molecular orbitals. So that would be 2. So if we choose 3 atomic orbitals here to do the LCAO, we will end up with 3 molecular orbitals for sure. Okay. And that's the case. For hydrogen molecular ion, we use 2 atomic orbitals to do the linear combination job, and we'll end up with 2 molecular orbitals. One for bonding orbital, another one for anti-bonding orbitals. Okay. And this S is overlap integral algorithm. Okay, hopefully it's still refreshing and fresh. Or I just talked about this in this week. Okay. Chapter 11, molecular energy diagram. That's how you set up, by using atomic orbitals with atomic molecules here, or orbitals, and construct the molecular orbitals, and fill in the electrons. Okay. And the only way for me to take care is the pattern here. So sometimes the sigma will be lower than 2 pi. Okay. But here, if sigma is higher than 2 pi, that simply represents if you have element before nitrogen or just nitrogen in the periodic table. Okay. And based on this figure, we can evaluate bond order, right? Now tell me what's the bond order for nitrogen?
30.
Okay, the number of electrons in bonding orbitals minus the number of electrons in the antibody orbitals divided by 2. Okay? And another thing is there's no unpaired electrons. So this is the one molecule regarding the magnetic property. Okay, so you cannot combine nickel nitrogen within the magnetic field. Okay, those are something we didn't talk about in lecture. Okay, we didn't talk about lecture. So here it is for completion. And this case is the oxygen one. Okay, if we have the element with oxygen or fluorine, the two, if we're talking about diatomic molecules, the two elements must be or oxygen or fluorine. Okay. If one is carbon, one is nitrogen, this should form the previous pattern here. Okay, so here, the sigma orbital energy is lower than the 2 pi bonding orbitals. Okay, this is due to sp mixing. Okay. And again, you can calculate bond order. That's 2 for oxygen. So simply means oxygen, oxygen have double bonds in between. And the magnetic property, they are paramagnetic molecules, so they can be confined within the magnetic field. Okay. So any question about this? Again, very important. And you can see that for some questions, if we ask you to construct the molecular orbitals to write up the diagram, you can just write this part. Okay, it's okay. In this lecture, we will mention that. You can just write it down.
Yes, any paramagnetic molecules, any molecule with a single subshell is unpaired, or if all subshells are unpaired?
If only one, if there's one. If there's only one unpaired, that should show paramagnetic. Okay, it does not to be a complete field. All right. So highly important again. Okay, you can just guess what question we can give you in this chapter. Right? It's pretty easy to predict. And this is the energy pattern. Okay, this energy pattern where you see the sp mixing, where you see the transition between nitrogen and oxygen. Okay, so you know when to change the sequence now. Okay. So you can get you can get the grand picture, but you cannot get into the detailed question. We can ask you in some weird way. So this is a heteronuclear diatomic molecules, and the special case involves hydrogen. So the problem is the hydrogen 1s orbital, we need to think about which orbitals from another atom has a comparable energy with 1s in order to be overlapped together. Okay. So in this case, it's actually the 2pz. So they form the bonding orbital, antibody orbitals, and other orbitals they form non-bonding orbitals. Okay. And one more thing I want to emphasize here is when you try to label each molecular state, so don't look at this illustration, it's a little bit tricky. Okay? When you want to label each molecular state, there's one thing you need to pay extra attention. You still remember? What is it? It's related to symmetry. No GI. Okay, no GI. For heteronuclear diatomic.
When do you know that it's a non-bonding orbital?
Oh, if you find this one, because one atomic orbital with another one atomic orbital, they can only interact with one by one. And not only. So if you choose that one, so that's something deals with the internuclear axis. We define that as z-axis. So in order to form the overlap with edge, you can only form it this way. So if you choose px or py, they form the cancel out.
So you have to know
keep mixing, which case takes priority? Like if there's one before nitrogen and one after, which one do you want?
Well, if you have two molecules, A and B, right? We're talking about diatomic molecule.
Yeah.
So let's say A and B. If one of the elements is above nitrogen, then you do not consider about SP of mixing. Okay? For example, what pattern? Nitrogen pattern. Okay? For example, what pattern? Okay, you understand that? Alright.
So, as far as bond order, what is the bond order of unpaired electrons, a single unpaired electron, like anywhere, or anti-bonding, most importantly? Like
Unpaired one is just one number. So sometimes give you 0.5 in bond order.
Okay,
That's possible because it's represented the bond between 2.5. It means the bond between triple bond and double bond. That's conjugation. Alright? One. Now, this is a little bit complicated. Here I just show you the overlap. Why we will give you a question in public is not about something when those good.
John, you?
Alright, and the bond order.
I think for heteroatomic, heteronuclear diatomic molecule, if one of them is before oxygen, you should follow the nitrogen.
And the nitrogen.
Right. So NO should be the nitrogen.
Nitrogen. Yeah. OF should follow the oxygen.
Okay.
Yeah. Right.
I just want to make sure.
Right. I messed it like that. Okay. All right. Okay. So again, yeah. If one of them is before nitrogen, follow the nitrogen. And here it talks about the bond order with bond energy, in relation to them. So we'll say if bond order increases, it simply means you go to like triple bond or even more, you increase the bond energy. You increase the bond energy, you increase the force constant. Okay? You increase bond energy, you decrease the bond density. So you decrease the rotational constant. You see the logic here? We actually mix in chapter 4, chapter 5, chapter 6 with chapter 11. So the joint point is here. Again, joint point is here. Okay. Final one is chapter 11. Wave function for conjugated molecules. You need to derive the Hacker determinate or the secure determinate to describe it. And again, in order to derive that, we need to label atoms, right? We label from a certain direction, from left to right or from right to left, wherever you want to go. 1, 2, 3, 4, and we'll fill in this determinant, right? And for the diagonal element, what element should you fill in? Alpha minus E. And for neighbors, neighbors, 1 is neighbor with 2, so 1, 2 here will be beta 2 and 2 and 1. Beta, okay, all of them are beta. Now what about strangers, like 1 and 4? 1 and 4. So you know how to fill in that, right? You know that? Clear? Okay, clear. And benzene ring, same thing. You do that like this one. And next step is, evaluation. Evaluation, you can solve the x here. You can assume x equals alpha minus e divided by beta. And you can solve x. Once from the x, you get all pi electronic energy states. And that's sort of the energy we're talking about. Okay. Anyone still cannot solve the circular determinate? If your answer is still yes, please go back to review linear algebra. Really urgent things, okay? And just to review how to solve determinant and how to expand it, okay? All right, so that's pretty much for the whole thing for the wave function, and just a tail of the review today is the quantum numbers. So I will go very quickly. So those are the 6 quantum numbers we meant to talk about in this quarter, okay? First thing, I hope you will be clear about the names. I know I did all the names for you, but please go back and fill in the names here, okay? What's more important thing is what fact or what quantities they determine. Okay. For orbital angular momentum quantum number, it determines the magnitude of orbital square root L plus L, L times L plus 1, h bar. And here h bar is outside of the square root. Okay. Similar things for S, similar things for J. And here something with M, M stands for magnetic. So magnetic quantum number defines the Z component of the angular momentum. Okay. So Z component simply means you project the angular momentum to Z axis and the projection. Okay, remember that? The projection. Okay. And here, most important part to derive term symbols is what are the possible values for all those quantum numbers. Right? For N is what? Can N be with 0? Okay. L 0 to N minus 1, not N. Okay. ML in general. Well, it means for first one. 0, plus minus 1, plus minus 2, and 2, plus minus L. Possible value for S may be single atom, single electron. Hydrogen atom, hydrogen electron. I have MS in general. Not plus minus 1. Absolute value of S is not 1. From negative S to positive S with the interval 1. Do you remember that? Right? If S equals 1 over 2, MS equals plus minus 1 over 2. Okay? J values in general. Yeah, you get it from L minus S to L plus S with the interval 1. Okay? MJ?
0.
No.
Plus minus.
No. From negative J to positive J with the interval 1. Alright? Okay, no sense, be clear. Once you derive term symbol, you need to use it. Okay? Term symbol, the first one is not a term symbol, it's called an optical notation, where it's just an L. So the same as you need to know the different symbols for different L values. Right? So L equals 0, symbol is S. 1, okay? Just keep in mind, okay, the first one is 0, not 1. So when you, like, for F orbital, L equals what? Okay? So don't think it's 4. And here's a term symbol for atoms to describe the electronic inner states. Electronic inner states. And the general form is 2s plus 1 as a superscript with L and subscript J. And for hydrogen atoms, you can reduce to small letters because it only contains 1 electron. And again, the term symbol, the symbol of L is the same. Okay, symbol of L is the same. And you can evaluate S, evaluate J. Okay, for hydrogen atom, what is S? For hydrogen atom, what is S? Not 0, 1 half, not 2. 1 half, only 1 spin up or spin down. MS equals plus minus 1 over 2, S equals 1 over 2. Okay, so 2S plus 1 is called spring multiplicity, always equals 2 for hydrogen atom. Okay? And L depends on the value. So here, based on this, we can derive selection rules. Okay, based on selection rules. So what are selection rules? Selection rules are just some restrictions about a certain transition. It's something like the restrictions for something, for example, UC Santa's first ring. So what are the selection rules? Not all day. From 6 to 10, that's the first one. On a weekday, on a school night, right? Have to go up? Must start from where? After 3 selections. So equivalently, if we're talking about electronics transitions, here are the selection rules. Okay, you must follow it. Okay, with derive it, because you just memorize those things. We will not give this to you. Okay? We will not give those to you. For molecule, develop it. Okay, somebody need to memorize that, and yeah, it's hard for you to derive. Hard for you to derive, but anyway, it's not just conclusions you memorize. So again, selection rules are just some restrictions. Okay? The transition must follow this in order to happen, thermodynamically. First rain must happen according to those things. So the rain yesterday does not count as the first rain, okay? Because it stopped after 10, or some good stop between 6 and 10. Okay? And this is the term symbol for many electron atoms. Okay, the only job you need to do is to find L, find S, find J. So here I already told you, if you want to find use L, small letter L to get L, you need to do the vector sum, which is really hard for you to do. So the very good way to do is to use a scalar sum, where you use FL values. Okay, same thing for S. You first use scalar sum to derive MS, and S will be the maximum MS. Okay. Once you get L, once you get S, that's for all J values. So that's the possible values for J. Okay, and you can do it, right? You write on this, write on that, don't write on that. Okay, not that. Okay, just this one. Okay. Well, you can actually write it down by yourself, like J values we already talked about. Right? From L minus S to L plus S with the interval of 1. Okay. Finish? Okay. Molecular orbitals, molecular term symbols, we just talked today. Okay. Find ML, find the S, determine G and U, that's about the symmetry of the inversion center, and plus minus, that deals with sigma states only, and that talks about in reflection. Okay. So I believe this is a little bit fresh to you, so you can just go back, check your lecture notes, and from the lecture we give you some detailed examples to derive the term symbol. Okay. So four steps: ML, S, G, and U, and also for sigma states, basically you need to determine plus or minus. Like for this case, this sigma orbital here, can you tell me the size of this one? If this is the internuclear plane, the plus or minus. So notice here is a plus, here's minus, here's plus. If you do the reflection, what will happen? You change the sign. You change the sign, that's negative. Okay? So sort of these things, just go review it. Right?
Do we provide plus and minus notation for sigma orbitals?
Yeah, you need to do that. Yeah, for sigma, you need to find the complete notation. Okay, so you need to divide plus minus. But for some states, if it's not sigma, you don't need to worry about that. Okay, for non-sigma orbitals, you need to determine ML, S, and G and U. That's all. Okay, but for sigma, additionally, plus or minus. Right? So make sense?
For heteronuclear, do we do star instead of?
Yeah, instead of G and U. You use star to represent the anti-bonding. Use not stars to represent the bonding orbital. Exactly. No G and U. Okay? So no G and U here, notation here, the total term symbol, you don't need to worry about G and U. Okay? Heteronuclear, that's totally. Alright, make sense? Make sense here? How's the rule? The priority 1 is higher than 2, 2 is higher than 1. Can you tell me what is rule 1? Maximum S gives you lowest energy. Okay. Can you tell me what is rule 2? So if S is the same, okay, if S is the same, we should choose L max as a minimum, as the most stable one. Rule number 3. If L and S are the same, sometimes good. Depends on the field, right? If more than half field, okay, max. If less than half field, small j. If just a half field, small j, or actually in that case, the most stable one will only has one j value, so you don't need to worry about that. Okay? Number 3. Those things will we give you in the final? Okay, so you know that, right? Alright? And for example, we can give you a question like that. Well, that's not the real question, but can you tell me which term symbol has lower energy? Or someone freak out. Oh, we have a question mark here, how can we tell? nitrous S, because the priority, the first one has the highest priority. So this one is more stable than this one, right? Second question, what is the question mark? S equals what? 2s plus 1 equals 1, right? S is what? S is 0. What is L? 3 or 4? 3. So S, P, D, F. The fourth one, but should have the number of 3. Because the first one is, you're pretty good at it. You should do well in S. Right? Oh, we will do well in the final. That's a real picture from last year's final exam. Hopefully, all of you will be that guy. But also, please check carefully. Check carefully. Yeah. And don't about that, okay? Do not ask questions about that. We're supposed to. And the time, pay attention to the time. And pay attention to trees. Sometimes we'll have the trees. Pay attention. Okay. So with that, one final favor I want to ask you, can we take a photo together?
On camera. Just kidding. Photo time. Let's make some noise. All right, on 3. Quantum. 1, 2. Everybody.